We're going to see the principle, different types, construction, actual working of a BLDC motor, advantage, disadvantage, and application of a BLDC motor. Now, what is the BLDC motor? A brushless DC motor is a brushless DC motor is a permanent magnet synchronous electric motor. It's a permanent magnet synchronous electric motor which is driven by the direct current. Also, it can be controlled by electronically controlled commutation system. So, a motor which has a permanent magnet which runs under DC. Also, it can be controlled electronically by using a commutation system. It's called as BLDC motor. Commutation is nothing but it is the process of producing rotational torque by changing the phase current in an appropriate time. See, commutation in this case, see, there are many for commutation. In BLDC motor is nothing but the process of producing rotational torque by changing the phase current. By changing the phase current at the appropriate timings is called as commutation. So we know what is called BLDC motor now. Now we will see the principle of BLDC motor. See, the principle of BLDC motor is nothing but it is similar to that of the conventional DC motor. It states that when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force or rotational torque. As a consequence of reaction force, the magnet will experience equal and opposite force. In case of BLDC motor, the current carrying conductor is stationary, current magnet always moves. There are different types of BLDC motor based on the design, based on the use. The current carrying conductor is stationary. Current magnet always moves. There are different types of BLDC motor based. In case of BLDC motor, the current carrying conductor is stationary, current magnet always moves. There are different types of BLDC motor based on the design, based on the use of sensor, based on number of poles, based on the type of power signal. We can divide the BLDC motors. Based on the design, basically we have in-runner brushless DC motor. You will be having the motor inner side will rotate, and we have the outrun BLDC motor. The outer part of the motor will rotate. Then, with the help of the censored brushless, also we have uncensored brushless BLDC. We don't have any sensor in that. Then comes the number of poles, single pole and also multiple BLDC motor. Based on the power signal, it's very important. Based on the power signal, we are using two types. One is sinusoidal, another one is trapezoidal brushless DC motors. Now the construction of BLDC motor. Here in BLDC, permanent magnets rotate, so it is always attached to the rotor. The current carrying conductors are present in the stator. See here, we take this as the stator. Here you will be having the current carrying conductor or windings. See, only with the help of the commutation technique, electrical energy is converted into mechanical energy. We already know what is called commutation. The main design difference between the brushed and the brushless motor is the replacement of mechanical commutator. See, actual commutator, mechanical commutator is replaced and it is made as electrical commutators. A BLDC motor is a type of synchronous motor in the sense that magnetic field generated by the stator and the rotor revolves at the same frequency. It is similar to that of the synchronous motor. See, the brushless motor does not have any current carrying commutators. Commutators are completely removed. The field inside the brushless motor is switched through an amplifier which is triggered by the commutating device. You will be having a controller. Also, you will be having an optical encoder. You will be having a controller. Then comes the outrunner. Outrunner is the magnetic field is a drum rotor which rotates around the stator. The outermost part is the outrunner. The permanent magnet will be in the outermost and it will rotate. This style of is preferred for application required for high torque and where high RPM is not required. Then comes the inrunner. The stator is a fixed drum in which the field magnet rotates. This motor is known for producing less torque than the outrun style, but is capable of spinning at a very high RPM. Along with this, you will be having an Hall sensor to sense the position of the coil and which coil is to be energized. That is done with the help of the Hall sensor. Now we will see the actual working of a Bldc motor. Consider an outrunner motor. This is the outrunner motor. Take this is a permanent magnet. It's north pole and south pole. See, there is a space between the stator and the rotor. So for simplicity, I am not showing here. Here you will be having an air gap. Okay. This is take this as 3 coils. We will be having 3 coils. So we will be having 2 into 3. We will be having 6 poles. Take this coil as A, B, and C. This is the basic outrunner Bldc motor. See, this working of Bldc actually is nothing but the force interaction. It is nothing but the force interaction between the electromagnet and the permanent magnet. It is the basic force interaction. Here, when this can be explained with the help of diagram. See, take this as the excitation current. Phase A, phase B, and phase C. We have time here. Okay, this is divided into time. Just take this as time, and this will be the current, excitation current. See, initially when A is energized, change the color. If A is energized, suppose if I am supplying when A is energized, remaining both coils are not energized. So this north pole will have the tendency to attract towards the energized coil. Take this as south pole and this is north. Okay, this north pole, which is a permanent magnet, will try to attract towards the south pole of the coil which is actually energized. When this north pole comes here, I will excite the second coil B. Then I will excite the second coil B. At that time, coil A and coil C will remain ideal. So now the south pole will come here and the north pole will be coming here. So this magnet will try to move towards the B coil. Then again I will change the color. Take green. Again, now if I excite phase C, phase B and phase A will remain the same. So the permanent magnet which is attracted at phase B will move towards phase C. Now the permanent magnet will be here. Here you will be having the south pole. There is one off rotation. The poles will be interchanged. Now the next off. Now again I must excite this pole to move here. If I again excite in the same direction, this is already north pole here. This permanent magnet has north pole here. Therefore, they will repel each other. So you won't get a continuous rotation. So This way of excitation is wrong. I must energize phase A, but in the opposite direction. So see, in the opposite direction. So at this point, I will energize A in the opposite direction, such that I will get the south pole in this side and the north pole in the other side. So this north pole in the permanent magnet has the tendency to attract towards the south pole here. Similar way, your B and C windings will be remain idle. After this, I will excite B in the opposite direction. Then I will excite C winding in the opposite direction. So until here phase B will be idle and phase A will be idle. You can see here again I will start energizing phase A in the opposite direction. This is how if we provide a pulse through a controller to this winding, automatically there will be a continuous rotation of the Bldc motor. This is the basic working, but there is some drawbacks in this. See here. So if you see in this working, only one coil is actually energized at a time, at a single time. Remaining two are not energized. So this may reduce the performance of the motor. Performance of the motor is actually reduced. Also, the continuous rotation of the motor is affected. To make the motor more effective, we must at least energize two coils. At least energize two coils to get a proper continuous rotation. If you increase the number of coils, and depending upon the number of coils, if you excite the sequence, you will get a smooth operation and a complete rotation of the motor. Consider the same rotor. Also you will be having the stator. See, there is an air gap between the stator and the rotor. Now take this as north pole and this is south pole. We will be having the poles here. This is A, B and C. Here you will be having north pole and south pole, which is by the permanent magnet. See, why we are doing this modification is the combining effect will give us more output, or the combining effect will give us constant torque. Okay, so we are doing the next modification. Let's draw the excitation sketch here. Take this as the current, take this as phase A, phase B and phase C. At the same instant, I am going to energize both coil A as well as coil B. If you see here, coil A is also energized, coil B is also energized. If I energize both coils, see here you will be having south pole, here you will be having north pole, here you will be having south pole, here you will be having north pole. So this north pole will have the tendency to attract. This south pole will have the tendency to attract in a faster rate when compared to the previous case, because only one coil is energized. So the magnetic effect is more when both coils are energized. So I am energizing coil A and coil B. So it will the permanent magnet will reach at the faster rate. Then at that time coil C is not energized. Then I must energize both coil B as well as C. When it reaches to the center portion, I must energize coil B and C. So take this as T1. At T2, I am energizing coil B. Also, I must energize coil C. See, coil B is on and coil C is on. At that time, coil A must be de-energized. So at this position, if you see, your north pole will stay here, the south pole will be somewhere in the opposite direction. Okay. Then for the next duration, I must continue to excite coil C, and I must excite this coil A in the opposite direction, because this next to coil C is coil A, but I must excite that in the opposite direction. See, at that time my coil B will be de-energized. Okay. Then now I am here now. Now I am here. I will be having the north pole of the permanent magnet here and south pole of the permanent magnet here. I must energize coil A and coil B in the opposite direction. At that time, coil C will remain in the de-energized state. Then coil B is extended. Coil B is extended. Then coil C will be in the negative direction. Then at that time, coil A will be in the de-energized state. This is how the pulse continues. See, in this case, two coils are energized, so the performance is slightly improved when compared to the previous case. But there is a drawback in this also, because we have to give two separate signals to energize two coils. Two signals are required to energize each coil. So some modification must be done in the stator coils, so that this performance can be obtained with single coil energization. Now we will see the slight modification in the previous motor construction. See, take this as the rotor in the outermost part, and we have the stator which is present inside. Take this as the permanent magnet north pole and south pole. We have poles on the stator. In this fashion, take this as A dash, B dash, and C dash. There is an air gap in between the stator and the rotor. Okay, here for simplicity I am not mentioning it. Then you will be having three windings. Let it be here winding 1. I am connecting A and A dash. Okay. Winding 2, I will change the color. I am connecting B and B dash. Then third winding, I am connecting C and C dash. Okay. Now I must have an additional modification such that I will be having only 3 ends at the final stage. So for simplicity I am drawing it outside the rotor, but actually it will be present inside the stator. Okay. Take this connection. Now we will see how it is connected. So take this as the A. This winding is connected to this part of the circuit. Then B winding is connected here, and one terminal is taken out as the B coil, and C coil is taken at this position. Okay, so at last you will be having only A, B and C. So after this modification, the motor will actually run as in the case of the previous case, as this, according to the performance, but it is enough that if you give only one signal to the coil. See, for example, if I take, I will change the color. if I give plus DC pulse signal here at coil A, current flows in this direction, it reaches A dash, then it will energize B coil and it will be grounded here. So there is a closed path between these two. So if with one signal I am energizing two coils. Okay. Similar way, if I energize B, if I give a positive supply to B, current will flow through B and it will reach the C coil. Current will reach the C coil, then it will be grounded here. So if I give a pulse signal to a single coil, and the coil which is adjacent to that is also energized. In that way, we are modifying the stator. Okay. So this modification will work similar to that of the same modification which is done here. The waveform is going to be the same, but we are going to give only one signal to the each winding. Okay. Then see, the major part here is this. If I increase the number of coils, there will be a smooth operation. There will be a smooth operation, and you will be having a continuous torque. You will be having a continuous torque throughout the operation of the motor. Here we are having 6 poles and 3 coils. If you increase to 6 coils, the number of poles will increase. According to that, we must give the firing pulse to the coil to energize, so that you are getting a constant torque throughout the operation. Okay, now see here, the major drawback here is what we must know is which coil is to be energized. See, this magnet is a permanent magnet, it rotates. So we don't know which coil is to be energized. And second question is when it is to be energized. So we must find which coil to be energized and what time it must be energized. So it is in a practical condition, it is quite difficult to identify that. So we require a sensor. We require a sensor circuit to find which coil to be energized and at what time. This sensor mainly used here is an Hall effect sensor. Sensor. This shows the position of the coil. Okay, depending upon the position of the coil, with the help of a controller, we can give the firing pulse. So here, let us take this as a controller. Controller is nothing but a combination of logic gates. Here you will be having a pair of switches connected to a single winding. Okay. There are many circuits. For simplicity, I am drawing in this fashion. See, there are 3 coils outside. This coil will be inside the motor. Either it will be in the star connected system or it is a delta connected system. Here I am drawing it as star. It can also be connected as a delta connected system. This is the motor. Okay. These are the stator coils. These are the stator coils. Here you will be having the rotor. Okay. Yes. See, here we are placing the Hall effect sensor. This is the Hall effect sensor. This Hall effect sensor senses the signal and it gives the signal to the controller. This controller decides which pair of switches to be connected so that the certain suitable coil is energized. Okay. See here, these are switches. Only one switch will be turned on of in each pair. Okay, we have 3 pairs. Only one switch from each pair will be turned on, such that two coils are connected. Okay, this controller will decide the switching pattern of this motor so that you will get a continuous speed as well as torque operation. This is about the working of BLDC motor. Now we will go the now we will see the advantage and disadvantage. Advantage is more efficient, and since the brushes are absent, efficiency is very high. It can accelerate as well as decelerate easily because it has low inertia. The motor cooling is by conduction method. It has high life and maintenance free. Then disadvantages, cost is very high. Since we have controller, we have sensors, cost is quite high when compared to the conventional motors. Mainly used for limited power applications and requires a complex driver circuit. If the number of coils are increased, the driver circuits will be complex. Main applications are computer hard disk and DVD players, hybrid electrical vehicles, industrial robotics, CNC machines, washing machine dryers, and normal domestic applications such as fans, pumps, and blowers. Thank you. We will see you in the next session. Welcome. In this session, we are going to see about synchronous motors. So we are going to see different types of synchronous motors, construction, working, advantage, disadvantage, and the application of synchronous motors. When a three-phase supply is given to a three-phase alternator, then it will work as a motor. When the speed of the alternator is around the synchronous speed, for example, if you take 1500 rpm, it is at the synchronous speed, then we will call it as a synchronous generator. If the alternator runs as a motor, then it will rotate at the same synchronous speed as that of the alternator. So such a device which converts electrical energy into mechanical energy and always runs at synchronous speed is called as the synchronous motor. So it is a device which converts electrical energy into mechanical energy which always runs at synchronous speed is called as the synchronous motor. The synchronous speed works only at the synchronous speed and it cannot work at the speed other than the synchronous speed. Also, if we increase the load, there will be a slight modification in the speed. The speed may slightly vary, but after some constant time, it will again run at the synchronous speed, ms. Coming to the types of synchronous motor, we will be having a three-phase synchronous motor and single-phase synchronous motor. The single-phase synchronous motor is also further divided into special motors called as reluctance motor and hysteresis motor. The basic principle of a synchronous motor is the concept of rotating magnetic field (RMF). This field produced by a stationary three-phase winding, as we seen in the three-phase induction motor, rotates in the space and it is called as the rotating magnetic field. The speed of the rotating magnetic field is given by 120 F divided by P, where P is the number of poles on which the winding is founded and F is the supply frequency. This we already seen in the three-phase induction motor. Construction of a three-phase synchronous motor. There is no difference between the construction between the alternator and the motor. Both are synchronous machines. Mainly it consists of two parts, one is the stator and another one is the rotor. The stator has the, here this is the stator, the stationary part. The stator has the three-phase supply, either it will be in the star or delta current. Then comes the rotor. Rotor is the field winding. See here, this one is the field winding. You can see here, field winding. Either the poles may be projected or it may be in the cylindrical type. Mostly projected pole types are mainly used as shown in this diagram. This rotor is excited by a separately excited DC supply or through the slip rings. Through the slip rings it can be excited. Then comes the working of three-phase synchronous motor. The basic principle is nothing but the magnetic clock. Magnetic clocking. See, when two unlike poles of a magnet come in contact with each other, there will be a tremendous force of attraction between these two. When the electromagnetic current is very high, the force of attraction will also be very high. If one magnet rotates, if you see in this diagram number B, take this as diagram number A. If you see in this diagram number B, if one magnet rotates, the other also will have the tendency to rotate in the same direction with the same speed. Since there is a lock between these two, this is called as the magnetic locking condition. Here we are giving three-phase supply. You will be having two poles, north pole and south pole. Because of this three-phase supply, there will be a flux produced flowing in this region. Now, see, if you take this as the motor, this is the stator, and inside this you will be having a rotor. Okay, this stator is supplied, the conductors present in the stator is supplied by a three-phase supply. So because of this supply, there will be a current flow and flux is produced. This flux is nothing but the rotating magnetic field which rotates at the speed of ns, which is the synchronous speed. This rotating magnetic field will produce the same effect as we discussed in these two diagrams. So this ns will also rotate at the speed of 120 f divided by p, as shown here. Coming to the actual working of three-phase synchronous motor, consider the stator poles are N1 and S1 as shown in the diagram. See N1 and S1, and they are rotating in the clockwise direction, with the speed of ns. We know the formula for ns. It is initially rotating. Initially we are taking this rotor as stationary. Since the rotor poles are excited, they will be having two poles, which is N2 and S2. As this N1 and S1 rotates at the speed of ns, these two N2 and S2 will not be able to catch up with the N1 and S1 because of inertia. Because of inertia, these two poles will not be able to catch up with the poles N1 and S1. So there won't be any magnetic locking happening at the initial stage. Also, after off cycle, there is an interchange of poles. You see here, S1 will come here, N1 will come here. So this rotor must be more quick to attract towards the poles, but because of inertia it is not possible. Also because of the speed, it is quite impossible to make the magnetic lock. So this synchronous motor is not a self-starting motor. So some modification, or somehow we have to rotate this rotor to come in contact with the stationary poles so that magnetic locking takes place. Once the magnetic locking takes place, the rotor will rotate at the speed of rotating magnetic field. So there is a procedure to start a synchronous motor. So we will see what is the procedure to start the synchronous motor. Initially, we must give a three-phase supply. Supply to the stator to produce the rotating magnetic field, which rotates at the speed of ns. Second is, you have to drive the rotor by by using the external means like diesel generator, or you may have a small type of small motors. Somehow you must drive the rotor in the same direction, direction of that of the stator, to match the speed nearer to that of the synchronous speed. You must match the speed of the rotor nearer to that of the synchronous speed approximately. Then the third point is the after matching the speed, now switch on the excitation of the rotor conductors. So the DC supply is given to the rotor to produce the ports. To produce ports. Here in the case it is N2 and S2. After some period, see if you make this possible, after some period, um, both the fields will be magnetically locked. Both the fields will be magnetically locked. So in other words, we can say both the fields will be pulled into synchronization. Then remove the external device. This is how you must start the three-phase synchronous motor. After starting, we can remove the external device so that after some period the rotor rotates at the synchronous speed itself as that of the rotating magnetic field. There are some methods to start the synchronous motor. One is using a small type of motors or using a damper winding. So along with the actual winding of the rotor, you will be having the damper winding. You can also use a slip ring induction motor to start the synchronous motor. Then you can use a small DC machine which can be coupled to the actual shaft of the synchronous motor. These are the four ways that you can start a three-phase synchronous motor. So what will be the comparison between three-phase synchronous motor and the induction machine? See, induction motor, the construction is quite complicated, but in the induction motor is very, very simple. Synchronous motor is not a self-starting motor, but induction motor will be having a rotating magnetic field. It is a self-starting motor. In synchronous motor, we require a separate DC source, but here in induction motor is not necessary. The speed will be always synchronous here, but speed will be always less than the synchronous speed. Speed control is totally impossible in synchronous motor, but induction motor is possible, but it is quite difficult because it is a constant speed motor. As the load increases, even though the load increases, the speed remains constant. Here the load increases, speed will decrease. Then the motor is more costly and it requires frequent maintenance. Here in induction motor, the motor is very, very cheap and it is maintenance free. And we have more amount of difference that you can actually go through. Then comes the advantage and disadvantage. Advantage is high efficiency at high speeds. Maintenance is also easy. Full torque, it provides full torque at lower speed and it is reliable and it gives a smooth operation. Disadvantage is more expensive. You require additional motors to start them. Starting is quite difficult. Some of the applications are air conditioning and compressors, mainly used for power factor improvement, as a condenser. Then it can be used in servo drives, robotics and aerospace applications. Thank you. We will see you in the next session.